Welcome back to the deep dive on Neural Intel.
Great to be here.
Today, we're plunging into a topic that's been buzzing across the AI world, revolving around a really pivotal figure, Ilya Sutskever. He's the former co-founder and, chief scientist of OpenAI, now at the helm of his own venture, Safe Superintelligence, Inc.
Right, SSI. Big news.
Absolutely. And his insights have profoundly shaped the field for, well, over a decade now. And his recent, very public departure from OpenAI has only intensified the questions surrounding the fundamental future of AI.
Definitely.
You've probably seen the meme, right? That intriguing phrase, what did Ilya see?
It's everywhere.
It really points to a significant moment, maybe a crucial shift in thinking within the AI community. But, beyond the headlines and the memes, what are the deep technical specifics he's actually talking about?
Yeah, that's the key question.
We're here to focus on the nuts and bolts, the code, the data, the architecture that really underscore his vision.
Indeed, and this is a particularly timely and I think critical discussion. Sutskever's views offer a unique and deeply technical lens through which to understand not just the current state, but the actual evolution of AI.
Right.
From its deep learning origins through the current scaling challenges, all the way to, well, the conceptualization of artificial superintelligence.
And our focus today, just to be clear for everyone listening, will be squarely on those core technical details, the underlying mechanisms, the implications for the AI systems themselves. We're not really getting caught up in the broader societal or philosophical debates today.
Exactly, which immediately raises a fascinating and I think important question for anyone trying to stay ahead in this field, right? What exactly are the technical breakthroughs and, maybe more importantly, the bottlenecks that define this current moment in AI? And what are the proposed solutions that someone like Sutskever, with his deep technical background, is now betting his entire future on?
Yeah, precisely. So our mission today is clear. We want to give you a precise, technically focused understanding of where AI is headed, according to one of its most influential architects. We'll explore Sutskever's foundational dogmas, his term that propelled early deep learning, the emerging challenges like peak data that are forcing a paradigm shift, and his bold predictions for achieving, genuine reasoning and ultimately superintelligence.
It's a huge scope.
It is. And throughout this entire deep dive, we'll keep a sharp eye on the technical how and why that often get overlooked in the more general discussions.
Sounds good. Let's dive in.
Okay, so the architect of modern AI. To truly understand where Ilya Sutskever is going, we kind of need to understand where he's been.
Makes sense.
Let's zoom back to the origins, because that's where the seeds of this current vision were really planted. Before the current buzz, before what did Ilya see? There was Ilya Sutskever's pivotal role in AlexNet back in 2012.
Right, AlexNet, a landmark moment.
Yeah. It wasn't just a step forward for deep learning. It felt like a seismic shift. AlexNet, this convolutional neural network, it didn't just advance the field. Some argue it resurrected it from what they called an AI winter.
That's not an exaggeration, really.
So can you pinpoint the technical breakthroughs within AlexNet that truly made it such a game changer? And how did that initial success set the stage for everything that followed?
Absolutely. AlexNet wasn't just, another neural network. It was a forceful demonstration of deep learning's immense, previously underestimated power.
Right.
Before AlexNet, neural networks were theoretically interesting, sure, but they often struggled with practical applications, especially in computer vision. The breakthrough wasn't really a single invention, but more a masterful synthesis of existing ideas, crucially powered by new computational capabilities.
Okay.
Technically, it was the first time we saw convolutional neural networks, CNNs, applied successfully at such a large scale. They used rectified linear units, real ears, as activation functions. Yeah, and that helped mitigate the vanishing gradient problem, which allowed for much deeper networks to actually be trained effectively.
Ah, okay. So deeper networks became feasible.
Exactly. But perhaps most critically, it leveraged the parallel processing power of two high-end GPUs.
Two GPUs. Back in 2012, that was serious hardware.
Oh, absolutely. And that allowed it to train on the massive ImageNet dataset, over 1 million high-resolution images, 1,000 classes. It's huge.
Yeah.
So this combination, the deep CNN architecture, the real U's, and that powerful GPU acceleration, let AlexNet achieve an error rate of just 15.3% in the ImageNet challenge.
Which was a massive improvement, wasn't it?
Huge. The previous best was something like 26.2%. This wasn't just incremental. It was a qualitative leap. It silenced a lot of skeptics and really sparked widespread interest in neural networks as a viable, maybe even the dominant path for AI.
So it proved the concept at scale.
It showed that with enough data and enough compute, these complex multi-layered networks could get state-of-the-art results. It fundamentally reshaped research priorities across the board.
That's a fantastic breakdown. So AlexNet proved deep learning could see, essentially. But Sutskever's influence didn't stop there. He then moved on to revolutionize natural language processing, NLP,
Right, the language side.
which ultimately led to the transformer architecture that powers models like GPT today. How did his work here, shifting from vision to language, build on those early deep learning principles? How did it lead directly to the generative AI we're all talking about now?
Well, the transition from AlexNet's success in vision to Sutskever's work in NLP, especially with transformers, was a pretty logical extension of that deep learning dogma that was starting to take hold.
Okay.
The core idea was still the same. Complex patterns can be learned by sufficiently large and deep neural networks if you feed them vast amounts of data.
Right.
In NLP, before transformers, the dominant models were things like recurrent neural networks, RNNs, and LSTMs, long short-term memory networks.
Yeah, I remember those sequentials.
Exactly. They processed sequences word by word, which limited their ability to capture long-range dependencies in text. And they were notoriously difficult to parallelize, which made training them really slow and inefficient.
Okay, so parallelism was a bottleneck.
A huge one. Sutskever's contributions, often in collaboration with others, were instrumental in developing the sequence-to-sequence model, and most significantly, the transformer architecture.
The famous attention is all you need paper.
That's the one. He co-authored it. The transformer introduced this revolutionary mechanism, attention.
Can you break down attention a bit technically?
Sure. Basically, it allowed the model to weigh the importance of different parts of the input sequence when processing each element. So instead of just looking at the previous word, it could effectively look at all parts of the sentence simultaneously.
Yeah. Okay. So not just sequential anymore.
Precisely. This parallelism, combined with what's called the self-attention mechanism, dramatically improved the model's ability to handle those long-range dependencies in text. It also vastly accelerated training times because computations could run simultaneously across the sequence.
Which fits perfectly with using more GPUs, like with AlexNet.
Exactly. It fundamentally enabled the scaling to the enormous sizes we see in models like GPT today. It was a technical shift from sequential processing to a highly parallelized, attention-based architecture that perfectly aligned with that scaling hypothesis, paving the way for today's powerful generative AI.
So it wasn't just about building impressive models, but about this underlying set of beliefs, almost guiding principles that informed how to build them, predicting amazing capabilities if you just had the right conditions.
That's a good way to put it.
Sutskever famously articulated what he called the deep learning dogma, which is pretty revolutionary at the time, wasn't it, given the history of AI?
It really was a bold claim.
He posited that a neural network with even just 10 layers could theoretically replicate any human task in a fraction of a second, given the right conditions.
Which sounded almost like science fiction back then to many.
Right. And this was rooted in a few key foundational hypotheses that really defined this era of deep learning. Can you lay out these core technical hypotheses for us? It's almost like discovering the fundamental laws of physics for this new computational universe he was envisioning.
That's a perfect analogy, actually, and a very apt description of the mindset. This deep learning dogma wasn't just some vague aspiration. It was built on several foundational technical hypotheses that have proven remarkably accurate in shaping AI's trajectory. They were like the guiding stars.
Okay, what's the first one?
The first is the connectionism hypothesis. At its heart, this is the belief that artificial neurons can effectively mimic biological neurons in their, let's say, functional essence.
Mimicking the brain.
Yeah. Sutskever and his colleagues realized that, fundamentally, artificial neurons with their weighted inputs and activation functions could be designed to behave quite similarly to biological ones, at least in terms of information processing.
Okay.
The implication here is profound. If we can sufficiently understand and replicate these functional principles of biological brains in artificial networks, then these artificial networks could, theoretically, become capable of pretty much all the things that we human beings do.
Wow.
It provides a powerful theoretical underpinning, drawing direct inspiration from neuroscience for designing increasingly complex and capable AI systems.
That's an audacious claim, suggesting we've kind of cracked a fundamental code of intelligence just by mimicking biology. But what are the specific functional principles of biological neurons that we think we've successfully mimicked in silicon?
Good question.
And just as importantly, what are the big biological aspects? maybe dynamic synaptic plasticity, or those intricate neurotransmitter systems that we're still technically struggling to replicate? And how might those gaps affect actually realizing this connectionism hypothesis fully?
That's an excellent, really granular question. On the similarity side, we've definitely mimicked the basic input processing output function pretty well.
Okay.
Both biological and artificial neurons accumulate signals, and if a threshold is met, they fire or activate. The concept of weighted connections, representing synaptic strength, is also directly analogous.
Right, the weights.
Yeah. Artificial neural networks learn by adjusting these weights, much like how biological synapses strengthen or weaken over time, Hebbian learning in neuroscience. We've also seen success in replicating hierarchical processing, where simpler features combine into more complex ones, kind of like how the visual cortex works.
Okay, so some core analogies hold up, but what about the differences?
Ah, the differences are equally crucial, technically speaking. Biological neurons are far more complex and dynamic. For instance, synaptic plasticity in the brain. It's incredibly rich and varied. It involves not just changes in strength, but also in structure and timing.
Right.
Our artificial neurons usually have static weights after training, or they update in a very simplified way. We also lack the vast and varied neurotransmitter systems that modulate everything in the brain: neuronal activity, network states, mood, attention.
We just have activation functions, basically.
Pretty much, yeah. Usually just one type per layer or model. Furthermore, biological neurons are incredibly energy efficient. A human brain runs on about 20 watts.
20 watts compared to...
A single modern GPU can easily consume hundreds of watts. It's orders of magnitude different.
Wow, okay.
We also miss the complex temporal dynamics and precise spike timing that might encode information in biological systems. And lastly, the biological brain isn't just neurons. It's this highly integrated system with glial cells, intricate feedback loops, neurogenesis, pruning, elements we haven't fully understood or replicated yet.
So these technical gaps mean that while artificial neurons can mimic some functions...
Exactly. They might lack the full spectrum of adaptive learning, robustness, and those emergent properties we see in natural intelligence without some truly novel architectural or mechanistic innovations.
Okay, that makes sense. What's the next hypothesis in the dogma?
Then there's the autoregression hypothesis. This idea posits that a seemingly simple task like next token prediction or sequence to sequence when scaled enormously could actually grasp the correct data distribution needed to generalize. Generalize from basic tasks like translation to broader, more complex intelligence.
So just predicting the next word, essentially.
Or pixel or code snippet, yeah. The implication is that this process, at massive scale, forces the model to build an internal world model. It suggests genuine understanding and reasoning beyond just, finding statistical correlations.
How so? How does predicting the next word force that?
Because to consistently predict the next element correctly across a vast and diverse data set, words, images, code, whatever the model has, to implicitly learn the underlying structure, the relationships, the rules of the data it's processing. It has to learn grammar, semantics, context, even basic facts about the world.
That's a big conceptual jump for many people, though, from just predicting the next word to actually forming a world model. Many still argue that while this approach creates impressively coherent outputs, it doesn't equate to genuine understanding or independent thought.
It's definitely a point of debate.
Can you technically break down how autoregression, through this massive scaling, is theorized to build this internal representation? What's happening inside the network that supposedly moves it beyond statistical correlation to what Sutskever implies is genuine understanding.
Right. It's not mystical, though it's still incredibly complex and an active research area. When an autoregressive model like an LLM predicts the next token across, say, a paragraph on astrophysics, then a dialogue from a play, then Python code, it's constantly being forced to learn the underlying dependencies, the causal structures, the semantic relationships in all that data.
Okay.
To accurately predict the cat sat on the mat, the model isn't just memorizing common word pairs. It needs an implicit grasp of objects, properties, spatial relations, maybe even basic physics, like animals sitting on surfaces.
So the pressure to predict correctly across diverse data forces this learning.
That's the hypothesis.
Yeah.
This pressure across an incredibly broad domain of human knowledge compels the network to develop internal representations that mirror the structures of the real world, or at least the structures present in the data describing the world.
Like the chess example you mentioned earlier.
Exactly. If you successfully predict the next move in chess consistently, you must have an implicit model of the board, the pieces, the rules. If you predict the next sentence in a scientific paper, you need an implicit model of scientific concepts, logical flow. The idea is that these implicit internal representations, accumulated across a massive, diverse data set, constitute a world model robust enough to generalize and eventually lead to forms of genuine reasoning. It learns about the world by predicting how it unfolds in language or other sequences.
That makes the world model idea a bit more tangible. But you mentioned the debate. Critics argue LLMs are just probabilistic guessers, great at interpolation within their training data, but they struggle with rigorous inference or out-of-distribution data.
Right, OD data, things they haven't really seen patterns for.
What are the specific architectural or training advancements that might bridge this gap between sophisticated pattern recognition and true AGI? Or, conversely, what are the inherent technical limitations of autoregression for achieving what we might call true reasoning?
This is precisely where the technical debate gets most intense and really critical for future AI development. Critics often point to hallucinations as evidence LLMs lack true understanding, right?
Yeah, making things up confidently.
Exactly. They generate convincing but factually wrong outputs, suggesting their world model is more like a statistical map than a truly generative causal understanding. Push them beyond their learned boundaries and they can fall apart.
So what could bridge that gap, technically?
From an architectural standpoint, one idea is integrating explicit symbolic reasoning modules. Instead of just relying on implicit stats, an AI could have components for logic, deduction, knowledge graph traversal, things it could call upon for specific tasks, kind of combining connectionist and symbolic AI.
Interesting, like adding a logic engine.
Sort of, yeah.
Hmm.
Another huge area is grounding in physical reality and feedback mechanisms, like we mentioned with AlphaZero learning from mistakes in simulated games.
Right, active learning.
Pure autoregression from static data doesn't give you that active, interactive learning. We might need architectures that let AI perform experiments, get explicit feedback from real or simulated environments, and update its internal model based on the consequences of its actions. Think reinforcement learning or embodied AI.
Okay.
The inherent limitation of pure autoregression, if it's not augmented, is that it might always remain derivative. It synthesizes existing patterns rather than truly innovating or discovering entirely new principles beyond its training data.
So the technical question is how to engineer discovery, not just synthesis.
Precisely. How do you get a system that can discover new knowledge? Not just rehash existing knowledge, maybe through an enhanced next token framework or something else entirely.
Mm.
It's about moving from just describing the world to interacting with and maybe even changing it.
Fascinating. Okay, what was the final hypothesis in the dogma?
Finally, we have the scaling hypothesis. This was arguably the most significant driving force behind all the recent rapid progress. The core idea, as Sutskever famously put it, was pretty direct. If you have a large, big data set and you train a very big neural network, then success is guaranteed.
Scale it up.
Basically, yeah. The implication was clear: the sheer scale of data, petabytes of it, and the computational power, trillions of operations per second, was seen as the primary lever. Just make everything bigger.
And it led to this exponential increase in model parameters, right? Millions to billions to trillions.
Exactly. And training data sizes ballooned too. And it did unlock capabilities that seemed unimaginable just a few years prior. Gave us models like GPT-2, GPT-3, and beyond.
And it certainly worked, at least for a while, leading to these monumental breakthroughs we're still trying to understand. But you noted it also leads directly to the challenges we face today, especially around data availability and compute cost. So what are the specific computational requirements for these very big neural networks and very big data sets that Sutskever talked about? And technically, what specific algorithmic or hardware innovations were absolutely essential to even enable this kind of scaling?
The requirements are truly staggering, mind-boggling, really. We're talking models with hundreds of billions, maybe even trillions of parameters,
Trillions.
trained on petabytes of text, image, audio data, basically, a huge chunk of all publicly accessible human digital information. This demands immense parallel processing power,
Which is where the hardware comes in.
primarily specialized hardware like GPUs, graphics processing units,
Right.
and Google's TPUs, tensor processing units. These chips are designed specifically for highly parallel matrix multiplications, which is the fundamental operation in neural nets.
Okay. And algorithmically.
Algorithmically, the transformer architecture itself, with self-attention, was a game changer. It allowed the whole input sequence to be processed in parallel, unlike those older recurrent networks that were sequential.
Right, enabling a hardware use.
Exactly. That parallelization was key to leveraging GPU power. Also, innovations in optimization algorithms like Atom and distributed training frameworks PyTorch, TensorFlow were crucial.
Oh.
They allowed researchers to efficiently distribute the training of one massive model across hundreds, even thousands of GPUs, orchestrating these gargantuan computations and memory management across entire data centers.
Wow. It's a whole ecosystem.
It really is. Without these synergistic advances in hardware, algorithms, and software frameworks, the scaling hypothesis just wouldn't have been technically possible. But this very success, this relentless pursuit of very big,
Yeah.
has now created the next set of really formidable problems.
Right. Which brings us to the data wall.
Exactly, the end of easy scaling.
So the scaling hypothesis, fueled by massive data and compute, was phenomenal. But what happens when that seemingly endless supply of human-generated data starts to run dry? Sutskever says we've hit peak data, marking the end of an era. What does this peak technically mean for AI development? It sounds like we're literally running out of raw materials for our best AI engines.
That analogy of running out of raw materials is highly accurate, actually.
Mhm.
What's fascinating is that data, once seen as this inexhaustible fossil fuel of AI, has indeed become a limiting factor.
Okay.
The massive pre-training data sets that powered GPT-2, GPT-3, they were largely composed of publicly available human-generated stuff from the internet, digitized books, archives.
Mhm.
These were finite resources.
Finite, right.
And as AI models got bigger and more sophisticated, their appetite for data grew exponentially. They simply started running out of unique, high-quality, diverse, human-generated data to train on.
It's not just volume, it's quality and novelty.
Absolutely crucial. Quality, novelty, and the rich diversity of human experience embedded in that data. This data bottleneck fundamentally alters a technical path forward. It forces a profound reevaluation of core development strategies.
You can't just scrape more web pages.
Pretty much. We're moving from an era of just collecting and processing more existing data to one where we have to engineer new ways to acquire or synthesize knowledge.
Okay, let's break down the technical impact of this scarcity.
Sure. Firstly, data scarcity means models have effectively consumed a huge portion of available high-quality public data. We've scraped the internet, digitized archives, processed tons of media. There just isn't an infinite supply of new, high-quality human content that these models haven't already seen in some form.
Okay, we've hit a limit there.
Secondly, we're definitely seeing diminishing returns. Simply adding more raw data, especially lower quality or redundant data, now yields less significant improvements in model performance.
Low-hanging fruit is gone.
Exactly.
Yeah.
The models have learned most general patterns from easily accessible data. Throwing more noise or repetitive info at them doesn't provide new insights. The implication is profound. The era of just scaling up by feeding more human data is, according to Sutskever, basically over. This necessitates a fundamental paradigm shift, a technical rethinking of how we acquire, generate, and leverage information for AI training. We can't just rely on passively consuming an ever-growing human digital library anymore.
If we've truly run out of these natural resources for AI, where does the new fuel come from? It's a critical technical problem.
It is.
Sutskever points to synthetic data generation and inference time compute as the new frontiers. What exactly are these technologies, technically, and how do they propose to bypass this peak data problem?
Yeah, that's the million-dollar question, maybe trillion-dollars. And these two areas are indeed the leading technical candidates for navigating this data wall. The future, as envisioned by Sutskever and many others, really lies in these critical areas: synthetic data generation and inference time compute.
Okay.
They are direct technical solutions to both the data bottleneck and also the need for more efficient and dynamic computation.
Let's start with synthetic data generation. What is that exactly?
Okay, this involves AI models generating their own training data, rather than relying solely on human-created data.
AI making data for other AI.
Essentially, yes. It could take many forms. An AI creating vast amounts of text, mimicking a specific style, generating photorealistic images for computer vision, synthesizing complex code, you name it.
The promise sounds enormous, an infinite customizable data supply.
Theoretically, yes. It could overcome the peak data problem entirely. However, there's a significant technical challenge and a big debate here.
The catch.
The concern that synthetic data will cause models to collapse.
Model collapse. I've heard that term. What does it mean?
It's not just a vague fear. It implies this potential cycle where models are repeatedly trained on data generated by prior generations of models.
Okay.
If you're not careful, this can lead to a degradation in quality, a drift away from real-world distributions, a loss of diversity, basically an echo chamber effect.
Like AI inbreeding.
That's a good, if slightly unsettling analogy.
Yeah.
Models might get increasingly good at reproducing the biases and limitations of earlier models, rather than learning true generalizability or adapting to new situations.
Okay, that's a serious risk.
It is. It raises a critical question for developers. What are the concrete technical safeguards or methods needed to ensure synthetic data improves rather than degrades model performance? How do you prevent this self-referential loop that starves the AI of true novelty?
That model collapse is a serious technical concern. It suggests a need for quality control or maybe a more dynamic learning approach.
Exactly.
So as a potential solution, some speculate Sutskever might be betting on curated data or maybe online learning with his new company, SSI,
That's plausible.
where the AI continuously learns from real-world interactions and feedback, not just static data sets.
Yeah.
From a technical view, what are the specific architectural requirements for that kind of robust, continuous online learning? How does it differ from traditional batch pre-training?
You've hit on a critical architectural shift there. The requirements for robust, continuous online learning are fundamentally different from those massive, one-off pre-training runs. Instead of a static snapshot of the world, you're designing systems that can incrementally update their knowledge. They need to manage what's called concept drift, where the underlying data changes over time.
Right. The world isn't static.
And critically, they need to prevent catastrophic forgetting.
Catastrophic forgetting. Sounds bad.
It is. It's a major technical hurdle where learning a new task or incorporating new data inadvertently wipes out previously learned knowledge.
Okay. So how do you prevent that architecturally?
You need highly adaptive memory architectures. Beyond just the long-term weights and short-term context windows we have now, maybe incorporating a medium-term memory, perhaps a dynamically evolving knowledge graph, or a fast weight system that can quickly encode new facts without destabilizing the core knowledge.
Interesting.
It also implies agent-based systems that can actively seek out data, perform experiments, get explicit feedback like reinforcement learning agents. Technically, this involves complex mechanisms for integrating new info without corrupting old knowledge.
Like what kind of mechanisms?
Techniques like elastic weight consolidation, EWC, or synaptic intelligence. They try to identify and protect the important weights in the network critical for past tasks, allowing new learning without undermining what's established.
Protecting old memories while making new ones.
Exactly. You might also see modular learning components, where new skills or knowledge domains are learned by specialized subnetworks that then get integrated, rather than trying to update one giant monolithic model.
Makes sense.
And of course, you need sophisticated validation systems to check the quality of the new online data and stop the model learning incorrect or biased patterns from transient interactions. It's about robust integration.
Okay, that covers synthetic data and online learning. What was the second part of the new paradigm?
The second part is inference time compute.
Inference time compute, what's that?
This involves a significant technical shift, doing more computational work during the inference stage, basically, when the AI model is actually being used to make predictions or generate outputs.
As opposed to just during training.
Exactly. Rather than doing almost all the heavy lifting during pre-training, this could involve more dynamic, adaptive computation during real-time interaction.
So the AI thinks more when you ask it a question.
That's a good way to put it. The implication is a move towards more efficient and flexible AI architectures that can think or reason more actively during application, rather than just retrieving info from a massive pre-computed knowledge base.
Okay.
It's about optimizing computation for dynamic, on-the-fly tasks, allowing the AI to engage in more sophisticated reasoning or problem-solving at the moment it's needed, not just relying on patterns absorbed during one big training run.
Like a human actively reasoning through a new problem versus just recalling a memorized answer.
Precisely. That's the analogy.
That's a fascinating distinction. How does inference time compute differ fundamentally from traditional model execution? And what are the hardware and software implications for doing this efficiently? Especially, given the slowing pace of Moore's law. It seems like this would need entirely new computational approaches. Maybe you could quickly unpack concepts like the von Neumann bottleneck for listeners less familiar with computer architecture.
Excellent point, yeah.
Yeah.
Fundamentally, traditional model execution is often about retrieving and applying pre-trained knowledge as fast as possible. The computation path is largely fixed once trained.
Okay.
Inference time compute, contrastingly, implies a capacity for active reasoning or dynamic problem-solving during output. Maybe the AI iteratively refines an answer, explores multiple logical paths, runs internal simulations to check its reasoning, calls specialized modules, all in real time.
Computational flexibility on demand.
Exactly. Now, the von Neumann bottleneck. This refers to the physical separation between a computer's processor, CPU or GPU, and its memory. Data constantly has to shuttle back and forth.
The data highway traffic jam.
Perfect analogy. It creates a huge slowdown, especially for AI models that are intensely data hungry, moving vast amounts of weights and activations. For inference time compute, where you want real-time adaptive reasoning, this latency is crippling because you're constantly accessing and manipulating internal states.
Okay, so how do we solve that? What are the hardware implications?
Significant. We need not just raw compute power, but highly efficient memory access. Specialized accelerators for things like graph traversal or symbolic logic might be needed, and potentially novel architectures that integrate processing and memory much more closely.
Like putting the kitchen right next to the pantry.
Exactly. Moving towards in-memory computing or processing in memory, PIM, to bypass that bottleneck. Even neuromorphic chips, which mimic the brain's structure by tightly integrating computation and memory, are being explored.
And on the software side?
It requires dynamic scheduling of computational graphs. Imagine an AI that doesn't just execute a fixed sequence of operations, but intelligently decides which parts of its network to activate and in what order, based on the specific query.
Like a smart task manager inside the AI.
Yeah. Dynamically rerouting calculations, maybe activating a symbolic module only when needed, dedicating more compute to explore a specific part of its world model. This is different from static optimization. It's dynamic adaptation during inference. Needs sophisticated internal monitoring, control loops, and new algorithms that can think with fewer steps or less energy.
Speaking of hardware constraints, we often hear about the end of Moore's law. How does this physical limitation on chip density impact the scaling strategies Ilya is talking about, both the old scaling and these new paradigms? And what does it mean for the sheer capital investment needed? This must be a huge part of what Ilya saw.
It absolutely is a major part of that vision of future constraints, yeah.
Yeah.
The physical limits of transistors mean we're not doubling chip density at that rapid pace anymore. The exponential growth has slowed significantly.
Okay.
This doesn't halt progress, but it fundamentally changes the economics and the technical approach to scaling. In the past, you got more compute by fitting more transistors onto the same chip, often with lower power per transistor.
Right. Denser and more efficient.
Now, if you want more compute for AI, especially for those very big networks,
Yeah.
or for more intensive inference time compute, you increasingly need more physical chips, not just denser ones.
So building bigger and bigger clusters.
Exactly. Which means exponentially higher capital investment for manufacturing, for building larger data centers, and critically, vastly greater energy consumption to power and cool them all.
A massive economic and energy challenge.
Huge. It's a critical, often overlooked technical and economic implication. It's not just algorithms anymore. It's raw silicon production, advanced packaging to connect chips efficiently, and the energy infrastructure. It creates a bottleneck requiring truly significant financial and engineering resources.
So from a technical perspective, these hardware constraints force us to look beyond just brute force scaling.
Absolutely. The reliance on more physical silicon means higher costs and potentially a hard physical ceiling if materials science or manufacturing don't see breakthroughs beyond traditional silicon CMOS tech.
So what architectural choices can mitigate this? How can models become more efficient?
This forces a rigorous reevaluation of AI model architectures. We need to find ways to be more algorithmically efficient. This might involve sparse models.
Sparse models?
Yeah, models that only activate a small fraction of their parameters for any given computation. Reduces the active computational footprint. Or developing more specialized architectures designed for specific computational patterns, not just general-purpose matrix math.
Tailored hardware software.
Right. There's also more emphasis on model compression techniques for deployment, shrinking models without losing too much performance. And looking further out, entirely new paradigms like optical computing using photons or quantum computing could offer ways to sidestep these limits by operating on different principles.
Okay, so we're hitting physical limits that demand smarter architectures, not just bigger ones, which kind of leads us to the next big topic, the leap towards genuine intelligence.
Right, beyond just scaling.
Current LLMs are incredible prediction machines, great at tasks based on patterns in their data. But Sutskever talks about a future with genuine human-like reasoning, not just sophisticated machine patterns. What's the technical distinction here? What makes genuine reasoning so profoundly different? It feels like a qualitative leap, not just quantitative. Another core part of what Ilya saw, maybe.
That's precisely the crux of his vision, I think, and a critical distinction. Current LLMs are, as you said, probabilistic guessers, exceptionally skilled at predicting the next token based on vast statistical patterns.
They function like they have a world model.
Exactly. They function like it, enabling coherent text generation, but it's still fundamentally derivative. They operate by interpolating, maybe extrapolating a bit, from what they've seen.
Okay.
Genuine reasoning, as Sutskever describes it, would surpass this. It implies the ability to truly innovate, form novel hypotheses, engage in abstract thought that goes fundamentally beyond interpolating existing data.
Generating new knowledge, not just remixing old stuff.
Precisely. Generating new knowledge, new ideas,
Mhm.
solving problems in ways not explicitly present in the training data, or even implicitly learnable through correlation alone. This raises that profound technical question. What architectural changes or learning mechanisms, beyond just scaling up transformers, are needed for an AI to transition from pattern recognition to this genuine reasoning?
Right. Let's delve into that technical vision. Sutskever suggests a key characteristic will be unpredictability.
Yes, unpredictability. He's quoted as saying, the more it reasons, the more unpredictable it becomes.
That's a profound departure from current deep learning, isn't it? Where responses are generally somewhat predictable, even if the specifics are novel.
It is. Genuine reasoning, in his view, implies this emergent capacity to generate truly unexpected solutions or insights, not just recombinations of existing knowledge. This unpredictability suggests a system that isn't just following learned patterns, but is dynamically constructing novel ones.
Okay. And that leads to the idea that this must go beyond simple next token prediction.
It likely must go beyond next token prediction alone, at least as we currently implement it. While Sutskever argued next token prediction could be enough for AGI at extreme scales, forcing that robust world model, achieving genuine reasoning, probably needs more.
Like what?
Some argue it needs grounding in physical reality
Yeah.
or robust feedback mechanisms. Think again about AlphaZero learning chess by playing itself, learning from outcomes.
Active engagement, not passive data consumption.
Exactly. That provides a richer, more dynamic learning source than static datasets. It allows for causal understanding, consequence-based learning, developing truly adaptive strategies, not just statistical correlations.
That makes sense. And you mentioned a biological analogy he uses.
Yes, the biological scaling analogy. He highlights the different brain-to-body scaling exponents in hominids versus other mammals.
How does that work?
For most mammals, brain size scales pretty proportionally to body size. But in the hominid lineage, there is this disproportionate growth in specific brain regions, like the prefrontal cortex, relative to overall brain size.
Not just bigger, but differently proportioned.
Right. It suggests a biological precedent for a different kind of scaling, a qualitative shift in organization or focus that led to unique human cognitive abilities beyond just having a bigger brain proportionally.
So AI might need a similar qualitative shift, not just more parameters.
That's the implication. AI might need to find analogous different scaling mechanisms, maybe a qualitative change in architecture or learning methodology to unlock new forms of intelligence, not just more powerful versions of existing ones. We need to look for architectural primitives that facilitate higher-order abstraction, maybe dynamic modularity, allowing an AI to reconfigure its thought processes for different problems, like how our brains engage different circuits.
That biological analogy is really compelling. It's not just about bigger, but differently structured intelligence, which naturally leads to AGI and ASI, artificial general intelligence, and superintelligence.
The big goals or fears depending on your perspective.
Sutskever famously warns AI will inevitably match all human abilities. He said, the day will come when AI will do all the things we can do. Not just some of them, but all of them.
A very strong claim.
But there's a huge debate in the technical community. Can current LLMs with next token prediction truly lead to AGI? Or is something fundamentally different needed? What are the specific technical arguments on both sides? And maybe clarify what the technical community generally means by AGI here.
Right, it's a definitional and technical battlefield. When we talk about AGI, generally we mean an AI with cognitive capabilities similar to or exceeding humans, learning outside training, generalizing across vastly different tasks, solving novel problems.
Okay, human-level cognitive flexibility.
Pretty much. On one side, some argue LLMs are inherently insufficient. They lack independent thought, true creativity, innovation beyond their data. Critics point to LLMs struggling with rigorous inference, formal logic, handling that out-of-distribution data effectively.
The hallucination problem again.
Exactly. Generating convincing prose without true understanding of causality or physics. These critics say without explicit causal models or real-world grounding, it's just a sophisticated statistical illusion.
Okay, that's the skeptic view. What's the other side?
Proponents, like Sutskever, contend that predictive power at extreme scale, perhaps augmented with feedback and other mechanisms, does lead to an internal world model so profound it effectively is intelligence.
Prediction is understanding at sufficient scale.
That's the argument. They believe as models grow, these internal world models become so sophisticated they'll spontaneously exhibit genuine reasoning and problem-solving, much like human intelligence emerges from complex neural nets learning from sensory input.
Okay, so within that debate, what technical ideas emerge for actually realizing AGI?
Several interesting perspectives. One view sees LLMs as a neocortex, a powerful component in a larger modular AI system.
Not the whole brain, just a part.
Right. Capable of decision-making, planning, but needing integration with other predictive subsystems, maybe for recursive memory, long-term knowledge, practically unlimited attention spans, or agentic capabilities for continuous interaction and learning from environments.
A hybrid architecture.
Potentially, yeah. Combining neural nets with symbolic reasoning or other paradigms. Then there's the hypothesis of self-improving AGI, often linked to a hard takeoff.
The intelligence explosion idea.
Exactly. The idea that once AGI is achieved, it immediately starts recursively upgrading itself to ASI superintelligence. The technical rationale is that increasing intelligence becomes an instrumental convergent goal, the best way to achieve any other goal more effectively.
Becoming smarter helps achieve anything else faster.
Precisely. The huge technical challenge there is designing initial AGI architectures that can self-modify robustly, safely, and in alignment with human values without totally unforeseen consequences.
A monumental challenge.
Monumental. And finally, there's the fundamental world model problem. How do you get genuine, adaptive, self-organizing behavior if the AI's model comes mainly from passive data, not active, embodied engagement?
The grounding problem again?
Yeah. Does an AI need interaction to fully grasp reality? Technical solutions might involve robotics, letting AI interact with the physical world, or highly realistic simulation environments where it can experiment and get feedback, grounding its knowledge in a more dynamic reality than just a data set.
Can it learn physics just from text, basically? Or does it need to drop the apple?
That's the core question. Does it need to drop the apple?
This all leads directly to Ilya Sutskever's new venture, Safe Superintelligence, Inc., SSI.
Right. The name says it all.
He aims to build safe AI and a safe supercomputer, explicitly saying it'll be insulated from typical market pressures. Given everything we've discussed, unpredictability, synthetic data issues, the world model problem, potential autonomy, what are the technical challenges for such a venture?
Huge challenges.
How do you technically build an insulated superintelligence system that remains safe and, crucially, predictable in its core alignment, especially if its very reasoning makes it unpredictable? It feels like the core paradox Ilya is tackling.
It is the profound paradox, absolutely. SSI's mission directly highlights this critical technical challenge of controlling and aligning increasingly powerful AI. Sutskever's emphasis on safety shows a deep understanding of the potential for emergent behaviors in superintelligent systems, behaviors that could be fundamentally unpredictable even to their creators.
Right.
He said he wants these systems to hold warm and positive feelings towards people. That's not just a vague ethical wish. It's a profound technical engineering challenge.
Engineering warm feelings.
Yeah,
How?
that's the critical question for engineering. Beyond theory, what are the concrete, implementable technical mechanisms to robustly insulate and control superintelligent AI, especially one capable of genuine reasoning and self-improvement, to ensure only positive outcomes? How do you do that without just crippling its intelligence? How do you build values into silicon?
Okay, let's get into the technical considerations for safe superintelligence. What does that actually involve?
First, there's superalignment. Sutskever's explicit focus on it, aiming for future superintelligent systems to hold warm and positive feelings towards people, towards humanity, acknowledges the immense technical difficulty.
It's way beyond bug fixing.
Oh, absolutely. It's about engineering values, ethical frameworks, right into the core architecture, ensuring its intrinsic goals align deeply with human well-being. This means developing incredibly complex utility functions and reward models that try to capture the vast spectrum of human values, ethics, long-term well-being, avoiding subtle harms.
How could that work technically?
Maybe techniques like inverse reinforcement learning, IRL, to infer human values from observing us, not just explicit feedback. Or recursive reward modeling, where an AI helps define and refine its own reward function in a human-aligned way. Maybe having meta AIs audit the reasoning process against human ethical frameworks, or using formal verification methods to mathematically prove certain behaviors are impossible.
Like constitutional AI.
Exactly. Constitutional AI is another example. Training an AI using explicit ethical principles, having it critique and revise its own outputs based on them. It's about designing an architecture that's not just powerful, but transparent and auditable in its values.
Okay, superalignment is one pillar. What else?
Second, robust control mechanisms. If AI becomes agentic and unpredictable, as Sutskever suggests, what kind of monitoring, constraints, or architectural designs can reliably keep it operating within desired parameters without stifling its intelligence?
It's a control problem.
Right. This is unprecedented. Maybe sophisticated sandbox environments to simulate and evaluate outputs before real-world deployment. Real-time anomaly detection for emergent behaviors, looking for deviations from expected thought patterns. Implementing red button mechanisms that can safely pause or revert an AI without causing catastrophic data loss, even if it resists.
Controls that a superintelligence couldn't bypass.
That's the goal. They need to be robust enough to withstand an AI potentially trying to subvert them. It might require continuous, high-fidelity monitoring, maybe by other AIs designed for oversight, and rigorous formal verification of critical control components.
And the third challenge?
Finally, the very act of defining AGI and ASI is a huge technical hurdle for safety. The vagueness around the definition, like cognitive capabilities similar to humans, makes it hard to even know when we've achieved it, let alone how to manage it safely.
If you can't define it, how do you measure if it's a line?
Exactly. This ambiguity is a technical measurement problem. If we don't have clear, measurable benchmarks for genuine reasoning or superintelligence, or more importantly, how we measure the alignment of such an intelligence, how do we know if our safety mechanisms are working?
Or if the AI is just faking alignment?
Precisely. Or if it's pursuing its own opaque objectives while appearing aligned. This needs deeper theoretical work on the computational nature of intelligence and consciousness to provide actionable technical metrics beyond just task performance.
Wow, okay, this deep dive into Ilya Sutskever's vision really illuminates the technical frontiers of AI. From those foundational dogmas that seemed almost simple but drove so much, to the challenges of peak data forcing a total rethink, and this pursuit of genuine reasoning, it's clear we're navigating a landscape evolving incredibly fast in its technical demands and architecture.
It really is, not just iteration, but fundamental paradigm shifts.
Indeed. What's compelling is that ongoing tension, isn't it? Between scaling the paradigms we have, which gave incredible results, and the urgent need for entirely new architectural data and even ethical engineering strategies.
Absolutely. The future hinges on solving these complex technical hurdles, from generating robust synthetic data that doesn't collapse, to engineering systems capable of truly unpredictable, yet somehow profoundly aligned reasoning.
It's a testament to the ingenuity and the sheer compute power driving this field, constantly pushing boundaries, but also demanding rigorous technical foresight and new ways of thinking at every single layer of the stack.
Couldn't agree more.
So what does this all mean for you, listening in and tracking these developments?
Well, the shift from data-intensive pre-training towards synthetic data and inference-time compute points to a future where AI systems aren't just bigger, but smarter, in fundamentally different, more dynamic ways. And the conversation about AGI and genuine reasoning, while maybe speculative, is rooted in very concrete technical challenges and opportunities. It demands innovation everywhere, from the silicon up to the algorithms. To really grasp where AI is going, you just have to understand these deep technical underpinnings.
Definitely. So considering Sutskever's assertion that the more a system reasons, the more unpredictable it becomes, and that critical technical challenge of ensuring synthetic data doesn't cause model collapse, plus the monumental task of truly engineering warm and positive feelings into a superintelligence, what truly unconceptualized technical advancements, maybe ones we haven't even begun to sketch out yet, will be necessary. Necessary to build genuinely reasoning AI that stays both robust and understandable without becoming this black box of emergent, uncontrollable intelligence. How do we technically engineer for the unknown unknowns that will inevitably arise from truly autonomous, superintelligent reasoning?
That is the question.
A profound thought to ponder as we watch this field evolve at lightning speed. To stay updated on the very latest AI and ML research papers and continue your own deep dives into these technical questions, make sure you visit our webpage, neuralintel.org, and check us out on YouTube.
We'll keep digging into these critical technical aspects.
Absolutely. We'll continue to explore these critical technical aspects of AI's journey, bringing you the details that matter most. Thank you for joining us on the deep dive.